Hey folks, I wanted to spend a little more time with 5.1 just graphing basic trigonometric functions, and I'm also going to talk about transformations on basic graphs. So really what I want you to be able to do is I want you to be able to graph sine x, cosine x, tangent x, cotangent x, and then also be able to graph secant x and cosecant x using sine and cosine x. And I'm going to show you that from the unit circle, and you just had to write down the unit circle on your last exam. So with that, basically, I just kind of want to remind you a few things about in function notation. Remember, the first column is your input, and your second column is your output. So the input deals with the x's, the output deals with the y's. So you input something into your function. We're going to input negative pi for the first example. So what's the sign of negative pi? Well, go to the unit circle. The angle is negative pi. That's the input. So where does negative pi go? Well, negative tells me I'm going in this direction over pi units. So it lands me right here. Sine is associated with the y values in the unit circle. So all of these are our sine values. Okay, so that means then that sine of negative pi is equal to 0. Sine of negative 3 pi over 4. Well, here's 1 pi over 4, negative 1 pi over 4. Here's negative 2 pi over 4. So here is negative 3 pi over 4. So sine of negative 3 pi over 4 is the same as 5 pi over 4. So negative 3 pi over 4 is equivalent to, and that's the y value, negative root 2 over 2. Okay, that gives us 2 points on the graph. So we've got that negative pi is equivalent to 0, and then negative 3 pi over 4 is somewhere between 0 and negative 1, kind of closer to negative 1. So we're going to put this point. Okay, the next one, negative pi, sine of negative pi over 2. Remember, negative pi over 2 is your input. So negative pi over 2 lands me, here's 0. Now I'm going in this direction because it's negative. Here's negative pi over 2 units because all the way across to here is pi units, negative pi units. So if I go halfway, that lands me at negative pi over 2. So remember, this is equivalent. 3 pi over 2 is equivalent to negative pi over 2. And that gives me a value of negative 1, which makes sense. So here, we're at the lowest spot that this graph is actually going to get. Okay, now at negative pi over 4, can you see that that's equivalent to 7 pi over 4? So now I say, okay, well, what's the sign of negative pi over 4? Well, what's the value, the y value that's associated at that point on the unit circle? It's negative root 2 over 2. So that brings me back to this point. Now, what's the sign of 0? Well, we go on the unit circle. Remember, the input is the angle measure. So here we are. That lands us here. What's the y value? There we go. It's 0. So sine of 0 is 0. Where does that put me on the graph? This is my angle theta, or your x's, this axis, and this is your output, or your y's. Okay, so that lands me here. Then what is the sine of pi over 4? So the sine of pi over 4 will go to the unit circle. And remember, pi over 4 is the angle. What is associated with that? Root 2 over 2. Notice that I'm not doing pi over 6. I'm just choosing these, and these will be fine. We can use these each time. I could do the sine of pi over 6, which is 1/2, which is right around here, right? So sine of pi over 6 would be like halfway between here. But I'm not going to because this is enough. I have enough points to graph. Now the sine of pi over 2 is 1. The sine of 3 pi over 4, so that lands us right here, is equal to root 2 over 2 again. So if we graph this, sine of pi over 4 is root 2 over 2. That's back up here. Sine of pi over 2 is 1, so pi over 2 is 1. And the sine of 3 pi over 4 is root 2 over 2 again. Sine of pi Now looking back here, what's the y value? The y value is 0. That makes sense. That lands us back down here. Okay, the sine of 5 pi over 4, well, that's right here. Sine of 5 pi over 4 is negative root 2 over 2. So that brings us down here. Sine of 3 pi over 2 from the graph is negative 1. Sine of 7 pi over 4, are you seeing the pattern? And back to 2 pi, remember 2 pi we complete the period, which it's called. It starts here and it finishes one full cycle back at 0. So now we can connect the dots and we have our graph from the indicated or the desired range, because we wanted to only go, I should say domain, because range always goes with the y values. So we're going to go from negative pi, I asked you, to 2 pi, and you can see the graph. What would the domain of this in this case be? Well, the domain that was given, we're assuming that theta is anywhere between negative pi and 2 pi. And just for fun, the range has to do with the y's. So think about this with the unit circle. See the farthest away that you can get from the center, and that's what we're measuring along this outer circle, is from negative 1 to 1. So we can say that the y values are between negative 1 and 1. And we already know this. We can say then the sine of x, even more specific, is always going to be less than or equal to 1 or greater than or equal to negative 1. And that's something that we established in I think it was chapter 1. A couple of other things I want to point out, because this is like a preview to 5.2. This, see how everything is centered around, in this case, the x-axis. So you can say that this is like the midline. I'm going to be using that word a lot. So the midline, and is a preview if you wanted to bump sine x up 2 units, your midline would change. So right now the midline is at y equals 0. But if you bumped it up 2 units with a plus 2, suppose that's my new function, all of these points would get bumped up 2 units. So the midline now would be at 2, and that would be off my graph because I expanded this. But the midline would be at 2, and you can draw a dashed line. Well, just for fun, let's just say the midline is at 1/2. So if I change that, oops, it's in between. So here's my midline now. And I'm going to bump this point up a 1/2 unit. So here it goes. Let's see if we can get a bright color for that. So we're going to bump this up a 1/2 unit. I'm going to bump this up a 1/2 unit. You see what I mean? So everything gets bumped up a 1/2 unit and everything is centered around there. So here, this negative 1 gets bumped up. So now this is at negative 1.5. And so you can kind of see the outline. And, excuse me, this one would get bumped up a 1/2 unit. So that would be back up here. So that's a better graph. And then from here, everything's getting bumped up a 1/2 unit as well. So at 0, we're bumped pi over 4. It's going to get bumped way up here. And it's not very accurate for that point, but this is a 1/2 unit. So it's up and then down. And then you can always focus, like, when does it go to 0? So here, you know that's true. And so that's often what I do, is I draw in my zeros when the function is equal to 0. And then from there, and I also know negative 1, so it's pretty easy to identify that this is 1/2 unit. So then you're going down here and up. Okay, so that's shifted up 1 unit. So now we're going to graph cotangent of x. And the deal with cotangent of x is, once again, just like with when we did identities, remember that cotangent of x, it's good to convert things into terms of sine and cosine. So cotangent is equal to cosine x over sine x. This will be helpful when we're inputting values, angle values, and getting an output. Because if I input negative pi, remember that's then what is the cosine of negative pi over the cosine of negative pi. Whoops, the sine of negative pi. So here's negative pi. Remember, we're going to go in this direction, negative pi units, so that lands us here. And in this case, cosine is always the x value, so we have negative 1 over 0. Uh-oh, what does that mean? That means it's undefined. So it's going to be undefined at negative pi. What does that mean graphically? Well, whenever you have a 0 in the denominator, that means that you have a vertical asymptote. So let's go out to negative pi, and we're going to draw a dashed line here for a vertical asymptote. Okay, so it's going to be x equals negative pi would be my vertical asymptote. So let's identify all the other vertical asymptotes. When is cosine in this, or in this case sine, when is sine going to be 0? Think about the angles. Sine is 0 at 0 when the angle is 0, and when it's equal to pi, it's equal at negative pi, at 0 again, at 2 pi, at 3 pi, at 4 pi, at 5 pi. Does that make sense? Because of this, anytime it's on the x-axis, which is at pi or multiples of pi, and the way that we write that in math, it's just k pi, because k could represent any number. It could represent, if it was 0, it would be at 0. If it was 1, it would be 1 pi. If it was 2, it would be 2 pi. If it was 3, it would be 3 pi. K has to be an integer. That's the other thing. Okay, so in this case, we know it's going to be undefined here and undefined here and undefined here. And that also means that we have a vertical asymptote at each of those spots. So vertical asymptote here, and I just go pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. That is equivalent to pi. So I'll just label the asymptotes for this. And then we've got 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. What's that? Well, that's 2 pi. So x equals 2 pi. And that's the farthest that we have to go in this case. Okay, so we know we have 4 vertical asymptotes in this domain that is given. And now we've got to figure out negative 3 pi over 4. Well, let's see if negative 3 pi over 4. So what is cosine? Let's make this brighter. What's cosine of, oh, that's much better, negative 3 pi over 4 over sine of negative 3 pi over 4. Well, where is negative 3 pi over 4? Here's negative 1 pi over 4. Here's negative 2 pi over 4, which is negative pi over 2. And here's negative 3 pi over 4. So that's equivalent to 5 pi over 4. What's the x value? That's negative root 2 over 2. So we got negative root 2 over 2 over negative root 2 over 2. Well, what's that equal to? That's equal to 1. That's kind of nice. So at negative 3 pi over 4, we are at positive 1. So I'm just going to go up here, because this is negative 1 pi over 4, 2 pi over 4, negative 3 pi over 4. Okay, and then let's figure it out. Okay, so we've got 1 here. At negative pi over 2, where are you? Well, that gives you this. Let's do a different color. So that lands you right here, negative pi over 2, which is 0 over negative 1. So you have 0 over negative 1, which is equivalent to 0. So that's another important feature on cotangent, is the 0, right? You always look for asymptotes and you look for intercepts. So this would be the x-intercept. Another word for that is 0. Where do you think negative pi over 4 is going to land? I'm going to guess it's going to land here, but let's show you why. So in this case, we're dealing with negative pi over 4, which is 7 pi over 4, equivalent to that, which if you look at the ratio, it's root 2 over 2 over negative root 2 over 2. Getting a little sloppy, but you get the point. So in this case, it's equal to -1. So now we're here at -1. So, and I should label, when you do this, at least set a couple of points so you know. So this is -pi/2 here. And then basically the nature, and you guys can just kind of memorize this, but it does get very, very large and very, very negative as it approaches these vertical asymptotes. Okay, in this case, we can kind of figure out that this, remember, is pi/2. And once again, at pi/2, you have 0/1. So we've got 0/1, which equals 0. And then once again at 3 pi/2, we're going to have 0/-1, which is equal to 0. So at 3 pi/2 right here, I've got 0. And then if you look at pi/4, which is right here, that's a ratio of the two same things. A number over the same number is equal to 1, and in this case they're both positive, so that explains this. And then look at 3 pi/4. Well, you've got one negative in that fraction, so that's going to land you here. So now you can draw the graph, and we should fill in the blanks. So we've got pi/4 was +1, 3 pi/4 is -1. You can guess that 5 pi/4 is probably going to be +1. 7 pi/4 is going to be negative. And you can check that out. See how there's one negative there? So we're going to go here and here. And of course there are points in between, like there is a pi/6 in there. But what is the ratio of √3/2/1? So if I, just for practice, if I said, what is the cotangent of pi/6? Well, that's √3/2/1/2, which is equivalent to the 2's cancel out, so you're left with the square root of 3. Well, the square root of 3 is somewhere between basically 1 and 2, right? So it's around that, in that ballpark, and that does confirm that here we've got pi/6 right here. So pi/6 is a little greater, and it would be to the left. So it's actually, yeah, a little up here. So you can do those values, but see, it's nice to just pick values that work for you that are nice numbers. That's why I gave you guys those specific tables. A couple of things I want to point out about cotangent and tangent. When you graph tangent, it's going to look pretty similar to that, only all of those lines, these little S's, are going to be going in the opposite direction. And the other thing I want to show you is that pay attention to the x-intercepts and also the vertical asymptotes. And then this period of tangent, we would say, doesn't really have a midline, tangent and cotangent, but the period of cotangent, it actually completes one full rotation. It completes the graph in pi radians. So do you see from here to here, we've completed one kind of graph that's the same, and if I repeat, if I bump up from pi to 2 pi, it's the same graph. So the last graph, I just want to demonstrate how cosecant is graphed. Once again, when you're going to the unit circle to look for values, think about 1/sin x. It's just so much easier, or the reciprocals. So I just like 1/sin x. And the other helpful thing when you're graphing these cosecant and secant is to graph sin x. And so we did that from before. And the cool thing about that is you can see that the zeros for sin x are here at -pi, 0, pi, and 2 pi. That means that if you think about it, and I'll bring it back, but there's a vertical asymptote at each of those. Because sin x, when is sin x equal to 0? Well, sin x is equal to 0 at 0 and at pi. That's in the denominator. So, and at -pi. So 1/0 would give me an undefined value, which is bad. So there's a vertical asymptote there. Same with 0 right here. So we're going to have a 1/0 So I guess technically this would be negative. No, it's positive. So it's just 1 over 0, which is undefined. And then once again at pi, 1 over 0, undefined. So you got your vertical asymptotes there. So identify the vertical asymptotes, and it's also nice to identify the zeros, but we're just going to sketch these vertical asymptotes. Anytime you have a fraction, whenever the denominator is equal to 0, that's when you have vertical asymptotes. Okay, the other important things, negative 3 pi over 4 again, that brings us, that's equivalent to 5 pi over 4 as said before. So now I've got 1 over negative 2 over, negative square root 2 over 2 because it's 1 over sine x, or 1 over sine of, we could even say 5 pi over 4 because negative 3 pi over 4 is equivalent to that. So if you flip that, you get negative 2 over the square root of 2, which is around negative 2.8. So we could say, okay, negative 2.8. So here we go, negative 2.8. And I don't really care too much about these values being specific. And in fact, my scale 1, 2, 3, 4, that would land me at 2. So that's going to even be off the map. But the point being is that this is your value. So here, the other cool thing now, why this graph is helpful, the sine graph, is that see sine is equal to negative 1 here. So, and that's at negative pi over 2. So here we are, we're down at 3 pi over 2 or negative pi over 2, which is the sine value at this point is negative 1. So you have 1 over negative 1, which is equal to negative 1. That's the same value here. So in this sense, we know that it's going to look like this. And if I continue on, so we're going in this direction. And then same, it would be equivalent here, and you can try it out. But we're looking at, once again at negative pi over 4, that's right here. So it'd be negative, it'd be 1 over square root of negative 2 over 2, which would land you down here. So this is the actual graph. It's not the sine graph. You use the sine graph, you dash the lines. And then you can actually just see the pattern because up here, if I finish these, and we'll just say it's negative 2.8, around that approximately, pi over 2 is going to be positive 2.8. Or excuse me, pi over 4 is going to be positive 2.8. So that's going to land me up here. And I think this time 1, 2, 3, 4, 2.8. So yeah, it's still going to be close to being off the graph. But you get the picture. This is equal to 1. So it's positive 2.8 approximate. And pi over 2 is sine of pi over 2 is 1. So 1 over 1 is equal to 1. So that's why the graph is nice. So then you can do this, and they're approaching these vertical asymptotes, getting really, really close, but not actually ever crossing them. And then the same goes for this, so you can see the pattern. And there are some nicer graphs in your book, but that's the idea for cosecant of x. So function notation f of x. Now just picture if you had f of x is equal to, maybe just for fun, let's change the pen color. How about f of x, or g of x, was equal to negative cosecant of x. So in this case, everything would be flipped. So if we do that, then we're going to go down here 1, 2, 3, 4. It's flipped about the x-axis. So here and here. And then up here, 1, 2, 3, 4, up here, here. That doesn't change your asymptotes, okay? And then up here, 1, 2, 3, 4. Now, I know that 5.1 has some transformations and that you haven't seen this. If you take pre-calculus, you're going to see it again. So what I recommend is I just recommend trying to do your best with the transformations, and you can always use your graphing calculator to confirm your drawing. So you do have an extension on this assignment and the quiz. So finish the quiz in 5.1. I hope this was helpful.